Welcome back to Mathematics. We're kicking off with a flashback question from the proof topic. We're trying to prove for positive x and y that 1 on x plus 1 on y is greater than or equal to 4 over x plus y. Okay, let's dive right in. Let's start off by multiplying everything by xy. The reason we can do this is because x and y are positive numbers, so we know that this inequality is not going to change signs because we know xy is a positive number. We're now going to simplify. Yeah, we're going to simplify the fractions on the left-hand side. X's and y's cancel out, and now we're going to multiply the x plus y across to the left-hand side to make x plus y squared. Greater than or equal to 4xy, we're going to expand the bracket on the left-hand side using a perfect square expansion like so. We're going to subtract 4xy from both sides, and then what do you know? We've got x squared minus 2xy plus y squared, which if we factorized it, looks like this. X minus y all squared, which we know is a true statement. X minus y is a number. If you square a number, it's going to be positive or 0. So all this in blue, we're doing on our spare working out paper in the exam, because technically our proof is meant to start with this bottom line, which is a known true statement. We work from the bottom to the top to reach the target required from the question. So this is the direction in which we write our proof in our actual exam to make sure that NASA doesn't cop any sneaky marks off us, the bloody dogs. Okay, today's lesson in mechanics is on simple harmonic motion. It's a pretty big one, so we'll see if this might be a two-parter or just a hectically long video, depending on how tired I get and how many mistakes I make. So let's dive in. Simple harmonic motion is the study of anything with periodic motion. This means something moving backwards and forwards, kind of like a pendulum oscillating from side to side, or looking at the tides of the ocean going in and out. Because of this periodic nature, the motion will always be described by some form of trigonometric function, cos or sine, or sometimes both. So this is the general form of our displacement of our simple harmonic motion. The definition of simple harmonic motion is defined as the acceleration being equal to minus n squared x minus c, n being the coefficient of your t inside your displacement functions, and c is the point at which you are centered around, which for a lot of questions will be 0, but for some of them we could be shifted up or down by c units. Don't forget that for any trigonometric function like sine or cosine, the period, which is how often this shape is repeating, is 2 pi divided by n, which hopefully you've experienced in the advanced course already, but that is a very important concept for all 3 calculus mathematics courses. Okay, so this is what simple harmonic motion looks like. Oscillations or repeated movements. The things that we're noticing is that on the endpoints where we're turning around, that's where we stop moving and turn around. So that's where our velocity is 0. Likewise, if you think about the point at which this object is moving with the greatest speed, it's when it passes through the center of motion, is when it's at its maximum speed. So just getting some more definitions on that. Here's our sine curve, for example. On the endpoints, we have our maximum displacement from the center of motion. That's where our velocity is 0 because we stop moving forwards and start moving backwards. And at this point where we're going from 0 speed, we are increasing speed at the greatest rate. So on the endpoints is where you'll find your maximum acceleration. At this point, our acceleration is negative because we're moving in the negative direction, or we're trending towards the negative direction. At the center of motion, that's where our displacement is 0, and it's where our speed is at its maximum because we're zooming past here. Is where we stop speeding up and start slowing down. So that's where our acceleration is equal to 0 because we are no longer increasing in speed, we start to decrease in speed. So these are all really important concepts that can make a lot of questions much simpler to manage. So having an idea of these 3 concepts on those 2 points is essential to finessing some simple harmonic motion questions. Such as this one, we have proved that this motion describes simple harmonic motion and find the period. So if we're trying to prove simple harmonic motion, we're trying to show the definition from the earlier slide that acceleration is equal to negative n squared times displacement. So we're going to go from our displacement to our acceleration by doing a bit of differentiation. So differentiation, cos turns into sine, or negative sine in fact, and we multiply by the derivative of what's inside our bracket, which is 3. So there is our velocity. We are going to differentiate this again to get our acceleration. So sine differentiates into cosine, once again multiplying by the derivative of our bracket, which is equal to 3. So this 15 turns into a 45. And now we are going to factor out of this because we want to end up with our x, our original displacement, which is right here. So we want a 5. So we're going to factor the negative 9 out of this. And I'm going to write negative 9 as negative 3 squared. What's left inside is what we started with, which is x. So we can write our acceleration equal to negative 3 squared x. So we have proven that our motion is acceleration equal to negative n squared x. This tells us that A, it is indeed in simple harmonic motion. So we've proven this. Also tells us that our value of n is 3. So our period is going to be 2 pi divided by 3, which is 2/3 of pi. Okay, next one, we are given our acceleration already in terms of x. We're trying to show simple harmonic motion, so we're trying to show that relationship once again. So we're going to take our expression and we're going to factor out a negative 16, leaving us with an x and a positive 1/4 inside our bracket. So already we have proven simple harmonic motion because we've got acceleration equal to negative n squared x plus or minus our center point. So this one is simple harmonic motion oscillating around negative 1/4 as our center point. Our value of n is 4, which means that our period is going to be 2 pi divided by 4. So our period is a half pi. All right, lovely. On to the next one. We have our simple harmonic motion according to displacement equal to 6 times sine of 2t plus pi on 2. First part of the question is find the velocity of the particle when it is first at the origin. All right, easy done. Let's go from our displacement to our velocity by doing, once again, a cheeky little bit of differential calculus. Sine turning into cos and multiplying by the derivative of the function inside the angle, which is equal to 2. So we end up with 12 cos of 2t plus pi on 2. Now we want to find when this thing is at the origin. So we want to find the values of t that make displacement equal to 0, because when you're at the origin, your displacement is 0. So solving this equal to 0, we get that the sine function is equal to 0 when your angles are, hang on, sorry, I'm just getting a call, go away. When our angles are 0 or pi or 2 pi, etc. like this. So we're going to subtract pi on 2 from all of these. So we want to solve this expression for t. So subtracting pi on 2 from everything and then dividing everything by 2, we get these expressions here. So our first time when we're at the origin is pi on 4 seconds. So we're going to sub t equals pi on 4 into our velocity to get an answer. So 2t becomes 2 pi on 4. This expression works out to be half pi plus half pi, which is pi. So we have 12 times cos pi. Cos pi is equal to negative 1, so we have negative 12. So when we are first at the origin, which is here, our acceleration is equal to our velocity is equal to negative 12. Okay, this question could have also been answered relatively quickly if you have a really good understanding of how to sketch trigonometric functions. So we have, if we factor the 2 out of our bracket inside our function, inside our angle, we have 6 times sine of 2t plus pi on 4. So if you know your stuff with trigonometry, you know that this means you have a sine function with an amplitude of 6, a period of 2 pi on 2, and we're shifted pi on 4 units to the left. So it looks like this. Ta-da! Okay, the last question was asking us to find the velocity of the particle when it was first at the origin, which is gone. Okay, cool. Part B we're going to use is find the first 2 times when the velocity is at its maximum. So, as I said in the intro, your particle is moving at its maximum speed as it passes through the center point. So, and we want positive velocity, so we want to be moving in the positive directions. We don't want this one because we're moving negatively. Here and here are the first 2 times where we are passing through the origin, which is when our speed is at a maximum and we're trending in the positive direction. So we're going to have our answers being 3/4 of pi and 7/4 of pi right here. Okay, so because we had a good idea of how to sketch this function, part B, we didn't need to use any algebra. We can just use our understanding of the concept of the motion and the graph, and we can get our answer relatively quickly. Okay, part C is find the particle's acceleration when it returns to its initial position. So initial position was here, starting at 6 on the displacement. We want to find the acceleration when it returns back to here. Okay, so we have our velocity, which we can get by differentiating x again, like we did in part A. If we differentiate once more, cos turns into minus sine, and we multiply by 2, and here is our expression for our acceleration. Okay, so we're looking at it right here. So this is when we return to our initial position, which is after pi seconds, okay? Because that's the period of the motion. Starting at 0, it takes pi seconds to return back to where we started. So we're just going to sub pi into our acceleration. And we can even take a shortcut if I remember my own slides. And at this point, as I said in the intro, at the endpoints where your velocity is 0, that's where your acceleration is maximized in the negative or positive direction. So because at this point, we are trending back towards the origin, so we are trending towards the negative direction, our acceleration here is going to be the maximum acceleration, and it's going to be negative. From this function here, we know sine is never going to be bigger than 1, so the maximum that this function will ever give us is negative 24 times 1, or negative 24 times negative 1. So because we know that, we don't need to do any algebra really, we can just say, all right, the maximum acceleration is going to be negative 24, because we are trending in the negative direction. Hopefully that makes some sense. Trying to go through these relatively quickly because there's like 4,000 examples, but here we go. Example 3 from Howard Mathematics, the OG. I love you, Howard. We have a particle moving in simple harmonic motion around the origin. When x is equal to 2, the particle is at rest. That's important because we know that particles are at rest at their endpoints. So there's a bit of a spoiler. When x is equal to 1, we have velocity equal to 3. We're going to find the values of a and n in our equation right here. So, like I said, when we are at our endpoint, we are at rest, which means that if x equals 2 is where we're turning around and stopping, that must be the amplitude of the function because we are centered around the origin. Okay, so because x equals 2 is where we're at rest, we're turning around, it's our endpoint, which gives us an amplitude of 2. So we straight away know that a is equal to 2. So there's our expression for x. We've just got to figure out what n is now using the other information in the question, which is that, okay, cool. Apparently velocity is equal to 2n cos nt. That's going to be useful if I remember. All right, so from the question, when x is equal to 1, so when this is equal to 1, the velocity of the particle is equal to 3. So our velocity expression is going to be equal to 3. What we've done here is we've created a pair of simultaneous equations that we can be really clever and solve for n, and so we can answer the question. So we differentiated displacement to get velocity, use the information in the question, and apply simultaneous equations. So the clever method here is we're going to divide 2n across to be underneath the 3. We'll divide both sides by 2, and now we have expressions for cos and sine. What we can do now is we can square those and say that cos squared is equal to 3 squared over 2n all squared right here, and sine squared is equal to 1/4. The reason I did that is because now we can do cos squared plus sine squared because that's our trigonometric Pythagorean identity. We know that's going to be equal to 1. So we can say, all right, cos squared plus sine squared is equal to 1. We know that as a fact. Now we have a little quadratic equation. We can solve for n, and then we've answered the question. So we're going to eliminate the fractions by multiplying everything by 4n squared. So we get 9 plus n squared equals 4n squared. We can subtract n squared from both sides to get 3n squared equals 9. We can divide both sides by 3. So we get n squared is equal to 3, which means that n must be equal to the square root of 3. Technically a plus minus, but we only really need a positive value for the purposes in the question. So there we go. We've got a, we've got n. So the equation of our motion would be x equal to 2 sine root 3t. We did it. Amazing. On to example 4. So before 2020, I suppose, simple harmonic motion was in the extension 1 course, and then in 2020 it got promoted to extension 2. So a few of the HSC questions from today's video are from old extension 1 papers rather than extension 2 papers. Okay, we've got a particle moving with its velocity given by this equation, relating velocity and displacement and some constant k. Show the particle moves in simple harmonic motion with period 2 pi on 3. Okay, so straight away, when I see v squared, I think to myself, well, hang on, if I differentiate v squared on 2, I'm going to get acceleration. That might be useful, so let's do that. We're going to subtract 9x squared across the right and say v squared equal to k minus 9x squared. That means that v squared on 2 is equal to this expression, just cutting everything in half. Now, if I differentiate v squared on 2, that's going to turn into, acceleration, as I promised, okay? So differentiating both sides, left-hand side turns into acceleration, the right-hand side turns into 0 minus 2 times 9x divided by 2. That turns into minus 9x. Now, because we know, what do we know? Because we are looking at simple harmonic motion, this is acceleration equal to negative n squared x. So looking at this, we can determine that n is equal to 3. So we've proven that the particle is in SMH, SHM, whatever, because we've shown that the equation works. From this, we can say that n is equal to 3, and so therefore the period is equal to 2 pi divided by 3, as required from the question. So So there we go. We did the acceleration here and we've got the period right here. Okay, another old extension 1 question. We've got our velocity related to our displacement given by this equation, moving in simple harmonic motion. Find all values for x for which the particle is at rest. So at rest is where your velocity is equal to 0. So we just need to find x values that make this equation equal to 0. So setting the quadratic equal to 0, we're going to divide everything by -2 to make it look a little bit more friendly. So we get x squared plus 4x minus 12 equals 0. We can factorize this into +6 and -2. So therefore, the two x values that give us a 0 velocity are -6 and +2. That's where we're at rest. Okay, final expression for the acceleration. Once again, we've got v squared. So to get from v squared to acceleration, we just need to cut it in half and then differentiate it with respect to x. So we're going to take our velocity squared, spoiler, we're going to divide everything by 2. So we get 12 minus 4 and minus x squared. Now this expression, if we differentiate with respect to x, we are going to gain our acceleration, which is equal to -4 minus 2x. So right there is our acceleration in terms of x. That gets us our second mark. Now for the last two, we are trying to find the maximum speed of the particle. So remember I said the maximum speed is when you pass through the center of the motion, which is where you stop speeding up and you start slowing down. So that's where your acceleration is equal to 0 because you have no change. So if we want to find the maximum speed, we really just need to look at where is our acceleration equal to 0, which is a nice and easy solve. We can solve this for x and we end up with x equal to -2. We're trying to find maximum speed, so we're going to substitute our displacement of -2 into our velocity to get an expression for v. So subbing -2 into our velocity equation from the question, we end up with the 32. So v squared is equal to 32. That means that v must be equal to the square root of 32. We're looking for the maximum speed, so we're looking at the positive case, which is going to be positive root 32, which is equal to 4 root 2, fun fact. So right there is our maximum speed because that is where our acceleration is equal to 0. Okay, for example 6, a bit more of a spicy one in parts. We've got a particle moving with this equation. This time it's involving sine and cos, so a little extra spice for you. Prove the particle is moving in SHM about x equals 3 by showing this. So for 2 marks, we're being asked to go from displacement to acceleration. It's all in terms of t, so we can just differentiate a couple times and just hope for the best. So let's do that. Let's start off by differentiating once to gain our velocity. So sine turns into cos, we multiply by 2 because that's the derivative of 2t. Minus cos differentiates into positive sine and we multiply by 2 once again. So there is our velocity. Let's differentiate this again to get our acceleration. So cos differentiating into negative sine, multiplying by 2 again, and then sine differentiating into cos, multiplying by 2. All right, we're trying to show that we are equal to -4 outside of x minus 3. So let's factorize out -4 out of this expression. So we get root 3 sine 2t, take away cos 2t, and now what's inside the bracket here is what we started with, just without the +3. So that means that this expression, root 3 sine 2t minus cos 2t, is equal to x minus 3 if we bring that across. So we've shown that what's inside here is equal to x minus 3. We've proven the conditions in the question, so there is our simple harmonic motion equation in terms of acceleration. Woohoo! Part 2, what is the period of the motion? So if we know our constant and we can look at this and straight away say, oh, this means that the value of n is 2 because we've got acceleration equal to negative n squared times x blah, 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 blah. We can say, all right, cool, n is equal to 2 because that's 2 squared. And we know that our period is 2 pi divided by n. 2 pi divided by 2 is pi, and there is our period for 1 mark. Part 3 is express the velocity in terms of this expression where alpha is in radians. This is an application of a method in the Extension 1 course called the auxiliary angle method. So if you already know how to do that, this might be old news for you, but just in case you don't know, we're starting off with our velocity, which we already established in part I. Now, we are going to look at this expression given to us in the question. We're going to expand this using our identity from the reference sheet. So hopefully this red thing here is somewhat familiar to you. Otherwise, this is going to be very confusing. Now, we are saying that velocity is going to be equal to this. So these two expressions are supposed to be equivalent. So if the blue line is equal to the red line, that must mean that a cos alpha is what's going with the cos 2t, which is the 2 root 3. Likewise, what's going with our sine 2t, which is the 2, that must be equal to a sine alpha. So those are our two equations, comparing these two and just playing matchups. These are two equations we are going to solve for a and alpha using a similar method from the example 2, I think. We're going to square both of these and say a squared cos squared is equal to 2 root 3 all squared, which is 12. And we're going to say a squared sine squared is equal to 4. If we add these together, on the left-hand side, we have cos squared plus sine squared, which is equal to 1. So the left-hand side is going to be equal to a squared. Right-hand side is equal to 16, which gets us that a is equal to 4. Again, could be plus minus 4, but we only need a positive case for the purpose of this question because it's an amplitude. Okay, now to find alpha, we could sub a equals 4 into either of these and solve. Or if you want, you can be a bit spicy and you can divide the two equations and say sine divided by cos is equal to 2 divided by 2 root 3. The 4's or the a's cancel out and you get sine over cos, which is equal to tan. And on the right hand side, we get 1 on root 3. So tan alpha is equal to 1 on root 3. If you know your magic triangles, then you know that this result is from alpha being equal to 30 degrees, which is pi on 6 radians. So we have our capital A, we have our alpha, which means we have our acceleration. No, we don't. We have our velocity formula given to us in the question, like this. All right, sweet, 2 marks, done. And on to the last part. Find all the times within the first pi seconds that the particle is moving at 2 meters per second in either direction. So we're taking our velocity formula from the last question. We want to find when is our velocity equal to positive or negative 2, because we're going 2 meters per second in either positive or negative direction. This is our equation to solve for 2 marks. We are going to divide both sides by 4 to get plus minus a half on the right. Now, cos is equal to a half when the angle inside the function is 60 degrees or pi on 3 radians. Because it's plus minus, it could be in all quadrants. So we're going to do quadrants 1, 2, 3, 4, etc. Okay, quadrant 1, 2, 3, 4. This is our expression for 2t minus pi on 6. Let's add pi on 6 to everything because we're trying to solve this for t. So adding pi on 6 across to every expression on the right-hand side, dividing everything by 2, and there we get our first 4 times that our velocity is plus or minus 2 from 0 to pi, okay? Because the next one would be bigger than pi, so I didn't write it. So there are our 4 answers for 2 marks. Okay, on to example 7, which is from the 2020 Extension 2 sample exam. So similar difficulty to what you are going to see in your exam potentially. Particle moving in simple harmonic motion. A particle is at rest between x equals -2 and x equals 8. So those must be our 2 endpoints because you are at rest at your endpoints. 6 seconds to travel from -2 to 8. Okay, cool. So we've got our displacement formula here. We're going to try and figure out some information so we can look at our velocity to find our maximum speed. So like I said, if -2 and 8 are our endpoints, that means the center of motion is halfway between them, which is equal to 3. Okay, if 3 is our endpoint, it means our amplitude must be 5 because 3 plus 5 is 8 and 3 take away 5 is -2. So we're going around 3 and we're going up by 5 and then down by 5 each time. So we have our 5 at the front, we have our +3 on the end because we're shifted up by 3 units. Now we're going to try and figure out our n. So it takes us 6 seconds to go from one endpoint to the other. And if you think in your mind about what a trigonometric graph looks like, if you're going from one peak to the other peak, that's half your period because to get back to the bottom peak, it takes a full period. Okay, that tells us that our period must be double 6 seconds, it must be 12 seconds. So again, from one low point to one high point is half a period, which takes 6 seconds. So the whole period is 12 seconds. You can see me tracing it out. If I took my job seriously, I'd have a graph here, but you get what you pay for at Mathematics. There's the period, and so period is equal to 2 pi on n, as we've established. If we solve this for n, we get that 2 pi divided by 12 is n, so n is pi on 6. Great, we have our equation right here. Now we have our displacement, we can differentiate it and look at our velocity, so we can have this turning into cos, and then we're going to multiply by the derivative of the angle, which is pi on 6. Here's our expression, and of course, whatever the number is at the front of your cos or sine, that's going to be your maximum value. So this function is never going to be bigger than 5 pi on 6, and it's never going to be smaller than -5 pi on 6. So it must be option A. Well done if you thought the exact same thing. You're a Goddamn genius. All right, for the last few examples, a very useful formula that we can establish in this course relates the velocity, the period, the amplitude, and the displacement of any particle in simple harmonic motion. So if your particle is moving in simple harmonic motion, this equation will always hold true. Velocity squared equals n squared, amplitude squared minus x squared. I would prove it to you, and trust me, I can. Obviously I can, but I'm trying to keep these as brief as possible, so we're just sticking to examples. If you want a proof of this, I'm sure there's a much better channel on YouTube right around the corner for you. Just trust me, this works. Okay, so looking at how we can use this, here's an old HSC question again. We've got our velocity squared equal to 25, 3 minus 2x minus x squared. Find a possible equation for the displacement as a function of time. So we're going to try and make this look like this. So we can figure out our n and our a, and we can write our equation. So we are going to take our bracket, we're going to factor the negative out of the x squared and the 2x to look like this, plus 3 just chilling on the end. What we're doing now is we are going to complete the square inside the brackets to get a perfect square, because we're trying to make it look all nice and factorized. So to make a perfect square inside here, I would love there to be a plus 1 inside the bracket, but because it's a negative at the front, I'm really adding a negative 1. So adding a plus 1 here means I've added a negative 1 into the equation. So I'm going to put a plus 1 at the end to keep the balance. So I've really only added 0 inside the bracket, and I haven't changed the conditions of the question. Now, 3 plus 1 is 4, and x squared plus 2x plus 1 is equal to x plus 1 all squared. So now it looks a bit more friendly. We can look at this and say, oh, cool, this means that if we compare it to this, we know that our n is equal to 5, we know our a is equal to 2, and we know our center of motion is at negative 1, okay, because we've got the x plus 1 in here. So n is 5, amplitude 2, center at x equals negative 1. That allows us to write our equation as something like this, okay? It's a possible equation, so it could be cos, could be sine. Who really cares? Sine's going to be good enough for me. A, n, and the center of motion. Another similar question, but with some little bit more spicy algebra. Again, we've got our velocity squared equation. We're trying to find an equation for x. So applying a similar method to the one from the last question, we are going to factorize the negative outside of what's inside the bracket, giving us x squared minus 2kx. Now, if I wanted to complete the square inside this bracket, half of the coefficient is negative k. If you square that, you get k squared. So I would love for there to be a k squared inside this bracket so I can do some factorization. So I'm just going to chuck it in. Here's a k squared. Again, there's a negative out the front, so it's really a negative k squared. So I'll just put a plus k squared there, and it's all good. Nothing's changed. I've only added 0. Put the k squared at the front, factorize this bracket as x minus k all squared. And now we're getting somewhere. We know that the value of n is n. That's fun. Our amplitude is k, and our center of motion is also k. So we can write our equation. This time I felt like using cos, but again, you can write sine. Who really cares? Amplitude of k, n value is n, and we're centered at plus k units. Okay, and now last and probably least, we've got example 10 from the 2021 Extension 2 HSC exam. So at the time of recording this video, this is as fresh as it gets. We've got our object moving in simple harmonic motion with our acceleration here. So straight away, we look at this and we say, all right, cool, that means our n value is 2 and our center of motion is at 3. That's pretty sick. Blah-de-blah, initial conditions, blah-de-blah-de-blah, between which two values of x is the particle oscillating. Let's tackle this. So finding x values where we're oscillating between, that's the endpoint of our motion, which is where our velocity is equal to 0. All right, cool. So if I can just get from my acceleration to my velocity, I can solve the velocity equal to 0, and now we're getting somewhere. So let's take our acceleration. This is in terms of x, so if I integrate it, I don't get velocity. As I've been over this, I've told you countless times, you get velocity squared on 2. So integrating this, we get minus 4x squared on 2 plus 12x plus c. Let's figure out the constant using some conditions. Object has speed of 8 when it passes through the origin. That means when velocity is 8, the value of x is equal to 0. So let's chuck them in. Solving this equation for c, we end up with c equal to 32. Just trust me, I checked the numbers. And now we sub that in, and we're going to multiply everything by 2, and there is our velocity squared. So the endpoints of our motion are x values that make our velocity, or our velocity squared, equal to 0. So let's solve this quadratic equal to 0. Factor out a negative 4 and do a cheeky little bit of factorizing, and we get x minus 8, x plus 2. So our endpoints between which we are oscillating is 8 and negative 2. which is good because it tells us our center of motion is 3, which we figured out before. But anyway, we'll get there. Next part for 2 marks. Find the verse value of t for which x is equal to 0, giving the answer correct to 2 decimal places. So to answer this question, we need to create our displacement equation, which means we need to get some information. So we got our acceleration. So like I said, we know that our n value is equal to 2 because this is n squared. We know the center of motion is 3, so we're getting somewhere. The endpoints are minus 2 and 8, which tells us that our amplitude is 5 because from 3 to 8 is 5 units. So that's our amplitude out the front of our sine or cos. So here's our possible equation. We have our value of t here. Sorry, we've got our value of n here. We've got our amplitude out the front, and we have our center of motion just up here. We've just got to figure out what alpha is. So let's use the information in the question once again. The object is 5.5 meters to the right of the origin and moving towards the origin initially. So that means when t is equal to 0, our x value is equal to 5.5. So let's chuck that in. We've got 5.5 on the left. We've got t is equal to 0. And so we've got 5 cos alpha plus 3 is equal to 5.5. This is the equation we're going to solve for alpha very quickly by subtracting 3 from both sides to get 2.5. Divide both sides by 5 to get 2.5 over 5, which is equal to a half. That tells us that alpha is equal to pi on 3. So now we have everything we need in our displacement equation. So we have this bad boy. All right, beautiful. That is a good looking displacement equation. Find the first value of t for which x is equal to 0. Answer to 2 decimal places. So we're just trying to find the value of t that makes this equal to 0. So we're just going to solve this trigonometric equation real smartly. Minus the 3 across, divide by 5. We're going to take cos inverse of both sides to look like this. So we get cos inverse of negative 3/5 is equal to 2t plus pi on 3. Now we just need to subtract the pi on 3 and divide by 2, and we're home for dinner. We get a value of t roughly equal to 0.58 seconds. And that'll wrap it up for 4 marks from 2021. Thank you very much. All right. Hopefully that helped you in some way. Sorry, it was a bit chaotic, but I'm pretty tired and it was like 100 examples. But here are some more examples to be found in Howard or Cambridge if you want some more study. But that'll do for now. Thanks for watching it. Catch you in the next video. Yeah, bye. Cheers.